Chapter 14, Section 3, the Fate of Pyruvate. Now, when it comes to the pyruvate, we see the pyruvate is going to end up in one of three places, okay? We can't just have a buildup of pyruvate from glycolysis. One, it's not good for cell. Two, during the generation of that pyruvate, the second phase, the payoff phase of glycolysis, reduced NAD to NADH. And, well, guess what? There's only a limited amount of NAD in the cell. So we have to take the NADHs and we have to regenerate NAD. Well, okay, so glucose, glycolysis turns it into pyruvate. And, well, what's going to happen now? A couple of things can occur. You can either go anaerobic or you can go aerobic. If it's anaerobic, pyruvate is going to be turned into lactate via lactate fermentation. It's going to be turned into ethanol during ethanol fermentation. During this process of fermentation of turning pyruvate, the 3-carbon pyruvate into 3-carbon lactate, or pyruvate into the 2-carbon ethanol and releasing of carbon dioxide, the bubbles in beer, champagne, bread, whatever. NADH will be oxidized back into NAD, and these anaerobic cells can then go through glycolysis one more time. And you just keep repeating this over and over. Lactate, the ethanol are byproducts, and this is what the primary thing is. Or if it's under aerobic conditions, go through, some NAD will be, NAD is reduced to NADH as you go from pyruvate to acetyl-CoA. Okay, this is the pyruvate entering into the mitochondria. You have this occurring. The 3-carbon pyruvate will be turned into the 2-carbon acetyl-CoA, and carbon dioxide will be released. Here's part of why you have to breathe out, releasing this carbon dioxide. The acetyl-CoA, through the citric acid cycle, these 2 carbons here will ultimately be consumed and release as carbon dioxide, and more NADs will be reduced to NADH. All those NADHs go to the mitochondria, electron transfer, oxidative phosphorylation, and the like. But here's what's going to happen to pyruvate. It's either going to become lactate, ethanol, or ultimately released as 1, 2, 4, 6 total carbon dioxides for every 1 glucose. Now that fermentation, this is what's happening and occurring under conditions that a cell does not want to or cannot go through aerobic cellular respiration, citric acid cycle, oxidative phosphorylation. Generally, we associate fermentation with anaerobic conditions, but there are some organisms that even in the presence of oxygen will go through fermentation just because that's what they're genetically programmed to do. The lactic acid, the ethanol, these are just ways to get rid of the pyruvate and in the process regenerate NAD by oxidizing NADH back to an NAD form. And that way glycolysis can go through another round, do it again, and so on. What they refer to as the Pasture Effect is an effect by the rate and total amount of glucose consumption under anaerobic conditions is many times greater than under aerobic conditions. Basically, you're going to yield some ATP from glycolysis alone. Boom. Then you do if you go through and you completely consume glucose down and releasing carbon dioxides. These organisms that are under the Pasture Effect have evolved mechanisms to make this a more efficient process. We do lactate fermentation. Only certain cells in our body can do lactate fermentations, lactic acid fermentation. We do it as a last, attempt to keep the cells going under anaerobic conditions. Certain bacteria we utilize, when we're making cheeses, yogurts, and whatnot, can do the same thing. They prefer oxygen, but under low oxygen, no oxygen conditions, they will shift over. But true anaerobes have come about where they can do this shift to lactic acid or alcohol fermentation in such a way that they can actually produce more ATP via their glycolysis than we could under ours. We see that in us, we don't do the Pasteur effect, but we can see this, what they call the Warburg effect. Something about cancerous tumors that have a high rate of glycolysis. You'll see increased lactic acid fermentation. So you see an increase lactic acid, lactate being produced, lactate or lactic acid being produced compared to other cells throughout the body. Now, most cells, like I said, just said in the last slide, most cells in our body have the ability there, but they don't very often. You don't do it in your skin because you're highly oxygenated there. You may do it, large muscle groups, yes. Some internal organelles, depends. Depends on what they're doing, and if they can do it, it's only under extreme conditions where, you're doing a lot of work and your blood oxygen level drops for short periods. Well, this turns out to be the basis of PET scans, PET scans. They'll go through, they'll shoot you up with radioactive dyes, sugars, and they're looking for over metabolism of certain cells. Basically, this lactate, fermentation, and then these radioactive molecules will collect, and then you just look for places that are dark in the PET scan. There, and those correspond to cancerous cells, also known as tumors. Pyruvate is the terminal electron acceptor in a lactic acid fermentation. Okay, pyruvate to lactate. Okay, if you look at these two, the only difference between pyruvate and lactate is what here is a carbonyl becomes a hydroxyl. NADH becomes NAD because the NADH via lactate dehydrogenase, nucleophilic attack on carbon 2 here. Going to transfer this hydrogen. You're going to split up these dual electron pairs, and then you have a hydroxyl carbon hydrogen. This is totally reversible. Okay, go through, do the reverse. Strip off the hydrogen. Take those electrons, put it back on NAD, reduce this to NADH, and then you have pyruvate that can. The trigger here, going left to right, pyruvate to lactate, is low to no oxygen levels. The trigger goes right to left, increased oxygen, or the availability of oxygen, which means that pyruvate can then go to the mitochondria, the citric acid cycle is still working. Oxidative phosphorylation is occurring. So this going glucose to pyruvate, this is glycolysis. Pyruvate to lactate, well, remember I told you back to the first slide of this section, NAD is in a set supply. Okay, this is our limiting factor. If all the NAD has been reduced to NADH, Well, the second phase of glycolysis gets stuck. You can't just skip this. This is part of the enzymatic reaction. So if there's no NAD available for those enzymes to utilize, the enzymes cannot complete the enzyme to product enzymatic step. Everything comes to a halt. So the pyruvate to lactate is a workaround. It's not a great workaround, but evolutionarily it's been around for a long time, so it's got to work. Take the pyruvate, like I said on the last slide, you take the pyruvate, and all you do is you break the carbonyl, make it a hydroxyl by stripping off this hydrogen here, oxidizing NADH to NADs, and you get lactate. You now have 2 free NADs, so the cell can go through one more round of glycolysis, generating 2 more ATPs. This is not a high energy thing for the majority of cells out there on this planet, but it is enough that the cell can limp along, metabolically speaking. For us, we do lactate fermentation, producing lactic acid in our major muscle groups, our legs, our back, our arms. Think about it here. There's a reason why they're showing this woman running. If you're one of those weird people who likes to go out jogging, you like to go out running, and you push it a little hard, you're having trouble getting deep breaths, you just cannot get in enough air, your blood oxygen level is going to drop. It's going to drop below a certain level. You're not going to have enough oxygen in your blood, not enough oxygen in your tissues, just not enough oxygen in your cells. Remember, oxygen is the final electronic acceptor of cellular respiration. No oxygen, or not enough, oxidative phosphorylation shuts down in the mitochondria. That shuts down. Citric acid cycle shuts down. Those shut down. That's one of the key triggers to go from normal cellular respiration and shunt pyruvate over to lactic acid. You build up lactic acid. That, as the last slide showed, this is just limping along. You're just creating enough ATP, regenerating just enough ATP to keep these cells going. Turns out, evolutionarily for us, we have receptors and whatnot in our muscles that recognize the buildup of this lactic acid, and it tells our brain pain. That's why you get muscle cramps. For most Olympic level athletes, what happens if you're out doing something, jogging, swimming, something, and you get a muscle cramp? You're going to stop or you're going to slow down. Deep breaths, reoxygenate your blood. Oxygen levels in the tissues go up. Oxygen levels in the cells go up. Oxidative phosphorylation in the mitochondria kicks in again. Citric acid cycle kicks in again, and then all that lactic acid, that lactate, gets turned back into pyruvate, and then pyruvate enters into the mitochondria, and everything's good to go. It's different, though, with ethanol fermentation. We're going to see this yeast. Some bacteria can do this. Pyruvate gets turned into acetylaldehyde. Acetylaldehyde. Tomato. Don't judge. So you're going to see with, couple of, you're going to have some helpers here. Pyruvate decarboxylase. This terminal carbon here is going to be released as carbon dioxide. I made the joke earlier on in this lecture that this is the bubbles. Yeah, this is the bubbles in bread. This is the bubbles in beer, champagne. It's right there. Leaving you with 2 carbons, acetaldehyde. Well, this, doesn't do you any good because remember, you're still maxed out here. All your NADs have been reduced. You're still stuck. So you take acetaldehyde, alcohol dehydrogenase, takes the NADs, adds them right there. Boom, boom, boom. take some hydrogens, oxidize NAD to H to NAD, and what was a carbonyl now becomes a hydroxyl. They keep saying this is reversible, but I can't think of many. Yeah, in the body, your liver, ethanol becomes acetaldehyde, but in the yeast that do this, I'm pretty sure this doesn't happen in their cells, but I could be wrong. What we're seeing here, when we look at pyruvate decarboxylase, okay, removing of the carbon, alcohol dehydrogenase. The alcohol dehydrogenase has a zinc finger in here that interacts with our 2-carbon thing here. We have NADH coming in. The attack here from this hydrogen to this carbon, this electron pair to this carbon, this one shifts there. So you end up with NAD, and behind my head you have 1, 2 carbon, one's methyl, carbon, hydrogen, and instead of a carbonyl, you now have a hydroxyl and another hydrogen also there. And it's all because of a zinc here in alcohol dehydrogenase that's interacting with the carbonyl group here, allowing for the attack by NADH. Part of the helper of this to occur is a coenzyme by the name of thiamine pyrophosphate. Thiamine pyrophosphate. It's a B1 derivative. This is utilized, TPP is also utilized to aid in the alteration of pyruvate to form acetaldehyde. Remember, that was the first step. Pyruvate with the magnesium, TPP gives you acetaldehyde, and carbon dioxide's released, or I'm sorry, acetaldehyde, then acetaldehyde, carbon dioxide gives you, ethanol. There are other TPP-dependent reactions other than ethanol fermentation. See it also, we're going to talk about it, and I believe it's the next section. We're talking the formation of acetyl-CoA. This is, remember, pyruvate entering into the mitochondria as it's passing through the organelle membrane, outer membrane. There will be a synthesis reaction occurring here as it's all going from outer through the inner membrane space and into the the inner, passing through the cristae membrane and all that. Fermentation, it's more than just the foods. I've mentioned bread, beer, wine, things like that. Cheeses, any dairy products that are taken from milk, cow, goat, I don't know what, camel, donkey, I've also seen. So, it changes the sugars, produces some form of lactic acid, which gives things that tart. And other organisms there can also imbue certain flavors, which is why most cheeses have slightly different flavors. We've also utilized the fact that this alcohol and lactic acid fermentation changes the pH. Not all organisms out there can handle pH changes, which is why we can store stuff. We utilize this when we make stuff like kimchi and whatnot, that there's going to be some fermentation occurring, and the change in the pH due to lactic acid or some other alcohol being broken down by organisms will change the pH, and the majority of microorganisms that would cause food spoilage can't handle it. Fermented food, you're going to see lactobacillus. If you go look at your yogurts and things like that, you're going to see some form of the genus Lactobacillus and then a species, Bulgaris Vulgaricus is one of the major ones, but there's quite a few other. Was it Lactobacillus philadelphus is one that's been genetically engineered by some food companies and whatnot. Propionibacterium fuderici ferments milk to produce things such as the Swiss cheese. As it's fermenting the milk, it's not doing lactic acid so much as doing a version of the ethanol fermentation, hence you get CO2 produced, while you get the bubbles, the air pockets in Swiss cheese. But like I talked about last slide, pickles, sauerkraut, kimchi, and many other things are based on the fermentation properties of microorganisms, and as a byproduct, keeps the food from spoiling due to other microorganisms being able to, break them down. We use fermentations in many different food preparations. Ethanol fermentation of carbohydrates, or from cereal grains and whatnot, gives us beer, which I'm sure many of you listening to this are very happy for. The alcohol fermentation is not always to generate ethanol. Sometimes it's things such as butanol, acetone, by say like Clostridium astrobutyranicum. Okay, this is done by industry to manufacture butanol, acetone. Different acids, formic acid, acetic acid, and whatnot. Take the ethanol, go through, do some different things to it. Boom, there you go. Excuse me, needed a caffeine hit. We're looking at fermentation as a means for producing fuel, biofuels. Take what would be biodegradable byproducts that still have a lot of energy in them, and go through and start breaking them down, utilizing microorganisms to break down, release starches, the sugars from the starches, and then utilize aerobic organisms that will then take those released sugars and produce ethanol. You then go through and distill out the ethanol, and now you have biofuel.